again to another video of Axiomatic Thermodynamics, and today we'll be talking about the different kind of state changes which are very widely used, as well as what a cyclic process actually is, before we move on to specifications of certain cyclic processes like Carnot or Stirling process. So firstly, we have already got to know in our first video what state variables are. Now, naturally, these state variables can be changed with time, and dependent on how you change the state variables, you will also get different type of state changes. So let's take into account some of the more widely used ones. Firstly, we have the isothermic state change, whereby the temperature remains constant. When the temperature remains constant, then one can obviously think of the fact that when it's an ideal gas, and we know that this relation holds, then when the T remains constant, then obviously PV, pressure times the volume, will also be remaining constant. So that would mean that because of the constants of T of temperature and PV also, the inner energy would be as follows. Because then the inner energy is actually zero. Right. So again, why is it so? Because as we defined before, the inner energy is basically the change of any of the inner energy is basically the sum of all the inner kinetic and potential energies of the microscopic systems of the particles, let's say. So if the temperature remains constant, that basically means that neither the kinetic nor the potential energy of the tiny systems, of the many degrees of freedom that they have changed. So that would mean that delta E is equal to 0, and the change of heat is basically minus the change of the work, and that comes from the first law of thermodynamics, as from the previous video. So we can, let's say, when we only take, instead of all those different state variables which we discussed about for work, we just take the volume and the pressure, then we would know that the change of heat is exactly equal to the change of volume from V1 to V2. And naturally, we can also write it as P times V2 minus V1, or as we know it, we can also use the ideal gas equation to convert this into nRT, natural logarithm of V2 divided by V1. How does this actually come to be? This can obviously be written in a shorter form here. Instead of the P, we obviously take the rest of the equation into account. So we basically have nRT divided by V times dV. And what is exactly the integration of 1 divided by x with respect to x? That's the natural logarithm of the variable. So that would basically be nRT, natural logarithm of v from v1 to v2. Right. So this is about the isothermic changes. What when what when the pressure is constant? And in that case, it is called isobaric changes. And in that case, the pressure remains constant. Okay, so what do we do now? Of course, again, the same theory applies. Since the pressure is constant, the work done would again be minus B delta V. Because since the pressure doesn't change, it doesn't really make much difference for us. And it would be minus V2 minus V1. So basically the change of volume. Right. Then we have the state change when the volume is constant, and it is called isochoric process, where volume remains constant. And that would now obviously change the situation, because we always said that delta W, which is the work done, is proportional to delta V. That would obviously become 0 now. So we have to somehow be able to explain the heat that is supplied, the inner energy of the system also, in terms of only heat. And that we say in these terms, that the delta E is equal to delta Q, because of course the delta W is 0 now. So delta Q, and that is done in terms of the degrees of freedom. So we explain generally that a degree of freedom being expressed with F divided by 2 N R and T minus T1. Right, this is a special definition that takes into account the equivalence of energy in different degrees of freedom in different directions. The degrees of freedom basically mean in how many ways is a system. For example, a particle able to move or express its movement. So let's say if we have a monoatomic gas, it basically can move in all 3 coordinate axes. So its degrees of freedom would be just 3. And right, so that would also mean that this is the sum of all its of all the heat as energy that has been supplied. And we also say that these terms in total, I can mark it with another color. This term in total equals CV, which is a specific heat at a certain volume. And this can obviously be also factored in the explanation for isochoric processes. Then we also have adiabatic, change of state of a system, whereby we say that delta Q is equal to 0, which means that there is no kind of heat as an energy that has been supplied to the system or going out of the system. In that case, the delta E will obviously be equaling delta W, and that would again in turn be equaling this equation here, right? So that would be F divided by 2 NR T2 minus T1. Right. There is of course also the choice of expressing it in terms of the adiabatic exponent, which is written using the Greek letter of kappa. How is it really defined? It is defined as 1 plus 2 divided by the degrees of freedom, which would basically make it as, if we calculate it now, f plus 2 on the top. And what would that make us? This would obviously just be, if we divide it by 2 again, it would just be, if you also factor in the r's, it would just be the specific heat capacity at constant pressure and divided by the specific heat capacity at constant volume. Whereby one can also say that in an adiabatic change you have PV to the power kappa I can again write in red, will be constant. Right. And then we come to the more important description of a cyclic process. A cyclic process is one where, like in a process in general, is where work is done. And generally in a cyclic process, you come back to the same position. That is the meaning of a cyclic process. How do we say that in terms of thermodynamics? We obviously consider, since P and V's are two very important state variables for us, we generally make our plots in a PV diagram, whereby we say, hey, if there is a cyclic process inside this graph, then the area that comes under this process is basically the work that is being done. And this basically correlates to the fact that work done is basically minus PdV. So since we have P in the y-axis and V in the x-axis, the integration, so basically the area under the curve would be the work. Right. And generally in terms of cyclic processes, we also use various heat baths. We call them heat baths or heat reservoirs. Those are basically objects with which the system in general would exchange heat. Obviously it doesn't apply for adiabatic processes, but it is in general also possible to have heat baths or reservoirs which supply heat to the system or take heat out of the system. Right, and two very good examples would be the Carnot process, whereby one uses isothermic and adiabatic. However, as you would have already by now thought of, adiabatic processes do not involve the exchange of energy, which is a bit difficult to realize in physical systems. So generally people try to come close to the Carnot process using the Stirling process, whereby they use isothermic and isochoric processes. Right. What the Carnot process and the Stirling process are, and what are the important stuff that are defined through those cyclic processes, will be talked about in the later videos. I hope this could clear a bit of doubts about the different state changes that happen in a system and the general definition of a cyclic process. So yeah, I would really like if you guys would like the videos and share it with your friends if you found it useful, and also comment on what could be changed and what I can add more into such videos. Thank you.